Okay, so can you hear me? Yeah, I guess so. So I would like to thank the organizer for giving me this opportunity. It's really great to be here. And so I would like to keep the talk a little bit informal, so please interrupt me if you have questions. Feel free to ask anything. So the title of the talk is Attacks and New Developments in Isogeny-based Cryptography. Oh, okay, now the microphone is on. What I said before is that feel free to ask me questions during the talk. So today I'm going to talk about what happened in isogeny-based cryptography. If you're familiar with isogeny-based cryptography, you know that the scenario has been changing lately. There have been new developments, and today I'm going to give you like a nice overview of these developments. So who am I? So I'm a PhD student at the University of Bristol. Here you can see Wells Memorial Building. It's not as nice as La Mole, but I think it's a nice building as well. I work in isogeny-based cryptography, which is a branch of post-quantum cryptography, a lot of fancy words altogether. But in practice, what do? I basically try to code up mathematical objects, like really algebraic geometry abstract objects. I try to code them up. And sometimes this computation, whenever I try to work with these mathematical objects, I mean, it takes me like a long time to run code and to learn experiments. And then eventually I realized that I was performing a lot of useless computations. So I'm really frustrated. Then I talk to people who are smarter than me, and they realize like, oh, actually, you can do this, and this other thing, and things will get way faster. And today I'm going to talk to you about when things get faster. So again, I said like post-quantum cryptography, a lot of fancy words. So let me set the scene a little bit. Post-quantum cryptography, here I'm going to semi-cite NIST, National Institute for Standards and Technology, the American National Institute. And they are kind of the institute for post-quantum cryptography. What's post-quantum cryptography? This is a branch of cryptography aiming at developing cryptographic systems that should be secure against both quantum and classical computers, so that's kind of a burdening task. We are not just caring about classical attackers, but rather to attackers, adversaries with quantum capabilities, so we need to be careful about what we should do to ensure that our cryptosystems are robust enough. And what's the additional requirement? Well, it's that these cryptosystems should be able to interoperate with existing communication protocols and networks. So not only they should be resistant against quantum computers, but they should also be fast. They should also be practical. In 2016, NIST initiated a process to develop and standardize new quantum-resistant protocols. There have been like many rounds, and at each round, some protocols fell. But now the algorithms that survived all this kind of scrutiny have been announced, and they will be standardized in the future. However, NIST is not really happy with what happened. I mean, like, they are looking for diversification among their crypto systems. And for this reason, they announced another standardization process. And the aim of this process will be, rather than generic, like, they will specifically focus on digital signature schemes. Okay, so I gave you a little bit of introduction about post-quantum cryptography. Now let me talk about, the basic protocol in cryptography, like a key exchange. So here we'll refer to the Diffie-Hellman key exchange. As customary in cryptography, we have two communication parties, and as customary, the names of the communication parties are Alice and Bob. So we start with G, a nice cyclic group generated by small g. So Alice got like a key pair given by a secret key, SKA, and a public key, GA. How does Alice generate this public key? So she takes the G, which is the generator of our cyclic group that we agreed on. It's like a public setup. And then she performs an exponentiation. So takes G, and using SKA, generates GA. Bob does the same with a different secret key. And then eventually, Alice will have her secret key, Bob the same, and they will share the public keys. And then Alice and Bob will share their public keys. And to agree on a common share key, Alice just exponentiates again by SKA, and Bob does the same for using SKB, and they eventually will agree on a shared key, which is this secret key K here. Everything is nice, everything smooth, and are we happy? Are we happy about this protocol? To be fair, yes, it's simple. It's fairly easy to understand, but we are kind of satisfied. There is like a small detail. What's the small detail? The small detail comes when we also take into account adversaries with quantum capabilities. Quantum computers are incredibly good at dealing with commutativity, and the reason why the protocol, the Diffie-Hellman protocol I described to you worked is because, we had commutativity. So if quantum computers are really good at dealing with commutativity, how can we have quantum-resistant cryptography? And specifically, why are we worrying about quantum computers? Because if we have our public key, G to the A for some A big enough quantum computer will eventually be able to retrieve the secret A in reasonable time. Here I've used the notation, I've used the word reasonable time, but what I mean here is polynomial time. As I said, I don't want to be hyper-technical in this talk, but I want rather give intuition about what's going to happen. So what does it mean in terms of the Diffie-Hellman key exchange? In practice, means that if we are given like a public key, and then any adversary with quantum capabilities will be able to extract the secret key. So how do we bypass this problem? How do we overcome this problem? Well, easy peasy. We use something which is non-commutative. Or even better, there is no structure at all. And now I'm going to give you like one of the potential solutions. So one of the potential solutions will use isogenies, and that's the reason why there is like the word isogeny-based cryptography in the title of my talk, otherwise it wouldn't make any sense. Isogenies are basically some special maps between some mathematical objects, and these mathematical objects are some really nice elliptic curves. What's an elliptic curve? Well, simply, it's an equation. We have an equation, and this equation is of the form y squared is equal to x cubed plus ax squared plus b. Actually, that's an x, not x squared, sorry, but that's fine. You can have elliptic curves of this form, but that's not the general form. That's a typo. Anyway, let's take things concretely. So an elliptic curve will have this shape, and the nice thing about elliptic curves is that you have a group law. How does this group law work? So basically, imagine that we have 2 points on an elliptic curve, P and Q, and how can we sum up these 2 points? Well, we draw a line passing by P and Q, we intersect the elliptic curve again with this line, and then we take the inverse of this point. And so summing P and Q will give you this point here. This group law is commutative. So as in the previous slide, I said that we don't want cryptosystems based on something commutative, otherwise they will be vulnerable to quantum computers. But there is actually another missing step that I will tell you later on, how to make sure that we are working with something which is not commutative. So here, if we have 2 points, we sum up the points in this way. But what about if we have just 1 point? So we take this point and we want to double this point, which means take P plus P. So rather than taking a line passing by 2 points, we rather draw the tangent line and the elliptic curve at this point. Then we intersect the elliptic curve again, and then we take the inverse. And this is like P plus P, which is commonly known as 2P. That makes sense as notation. But look at this point here specifically. This point is a little bit weird compared to the other one, to P, because if you draw the tangent line, it will be horizontal. So it will not intersect the elliptic curve again. What does it mean? To be a group, you need an additional datum, which is like the identity point, which means that if you take this point T and you double it, then the double of this point will be the point at infinity, which is the neutral element in the normal group law. And this is what we need to remember about elliptic curves. Now let's do like another step Step further, let's introduce in the scene some more complicated objects, isogenies. What's an isogeny? So I've described to you what's an elliptic curve. An isogeny is basically a map between two elliptic curves. So we have one elliptic curve here, another elliptic curve here. The good thing about these isogenies is that if you want to describe an isogeny, you just need a kernel of a map. Because, I mean, this is specifically, if you're a little bit familiar with maths, and morphism between varieties. So the only thing that we need to remember, to define uniquely an isogeny, you just need a point. So in the previous slide, I showed you this special point here, which if you double it, you will obtain the point at infinity. And now let's try to understand how, like, the isogeny, whose kernel is given by this point t, look like. So we have this point t. So this point t, since it's in the kernel of this special map, will be sent to the point at infinity, and that's the reason why you have this dot arrow, because, I mean, it goes to the infinity. And then, so the order of this point is a point of order 2, which means that an isogeny of this type will be a 2-to-1 map. So you take some point which differ by t, and then they will be mapped onto the same point on the image curve. And the same, I mean, this is just an example. This is how you can imagine, like, an isogeny between elliptic curves. It's something really explicit, something that you can actually mentally visualize. The other thing is that depending on the order of the kernel, this map will have a degree. So this map is a 2-to-1 map, because, I mean, the kernel of this map is actually a point of order 2. If we increase the order of this point, so imagine that this point, the kernel in the isogeny will have order n, then will be an n-to-1 map. Then, okay, so this is like an isogeny, and then specifically, if an isogeny maps E to itself, then this is an endomorphism. And here, we denote the set of all endomorphisms by this notation here, and E. And the set of all endomorphisms, together with zero map, which is the map that maps all the points to the infinity, this is a ring. And in particular, if this endomorphism, if the endomorphism ring is non-commutative, and that's what we need actually for cryptography. I mean, if we want to have quantum-resistant cryptography, we want to ensure that the objects we are dealing with don't have structure, or they have, like, really little structure. So once we have that this endomorphism ring is non-commutative, we call this curve supersingular. And this is what we are going to need to introduce the next, what I need to introduce the next cryptosystem. So here I'm going to recall you what's the cryptosystem in isogeny-based cryptography. This is kind of a drop-in replacement for the Diffie-Hellman protocol I've introduced you before. And this is called Supersingular Isogeny Diffie-Hellman. And shortly we will note it with SIDH. So as in the protocol that I've explained you before, in the example I've given you before, you have some setup. In this case, the setup will be a curve here, and then we have some points on this curve. We have 2 points, PA and QA, generating the A torsion of this curve, which are basically all the points, such that if you multiply these points by A, you obtain the element at infinity. And then you do the same for B, another integer, and you pick, like, 2 generators. These are, like, public parameters. And now again we have Alice and Bob. In this case, Alice and Bob, so we'll have some differences. So we will be different to the previous Diffie-Hellman protocol I described you before. The secret key here, in this case, will be an isogeny, whereas the public key will be like the product, like the image of this isogeny. Let me be, like, more concrete, and let me be, like, more explicit. So let's just analyze what Alice does. So Alice takes, like, the starting curve is 0, takes PB and QB, then she generates this isogeny phi A, and to generate this isogeny, as I said before, you just need the kernel of this specific map, which is given by, which is secret, and it's something that just Alice knows. So Alice computes this isogeny. She will end up on an elliptic curve. Let's call this elliptic curve EA. And then she maps PB and QB under this isogeny phi A. Bob does the same. So here in red, I mean like the secret elements, whereas in green, like the public elements. So the public key will be given by the curve EA together with 2 points, phi A PB, phi A QB. Bob does the same, and rather than just using PA and QA for the kernel of phi A, he will use PB and QB. So this is how you generate like a key pair. Then how does it work for the key exchange? Well, then Alice will take Bob's public key, and she will apply her secret, will compute again her secret isogeny phi A, and she will end up in this curve, EBA. Bob does the same using Alice's public key, and they will eventually end up in the same exact elliptic curve. And this is the shared key. So just to recall, Alice's key pair is given by this secret here, which describes the kernel of her isogeny, and the public key will be given by an elliptic curve together with 2 points. The same for Bob. This is a like really nice, neat idea. And I mean, let's just discuss a little bit about the cryptanalysis of this idea. I mean, what can we do with this protocol? Do we believe this protocol is robust enough? Well, we don't have structure on the public key. I mean, not enough structure. Actually, we do have structure, but not really that much structure. So you may think that it's kind of quantum safe. So what's the problem underlying SIDH? We are given like 2 supersingular curves, E0 and EB. Assume that we want to attack Bob's secret key. We have an isogeny, and then we are given like the map of some points under this isogeny. If we are able to recover the isogeny phi B, given like the public key, the image of these points under the secret isogeny, there we break the protocol. This assumption has been studied for like 10 years, and this protocol, SIDH, was really successful in the NIST competition because it enjoyed like really compact public keys, really short public keys, and also it was quite fast for isogeny standards, actually. Here we are talking about public key cryptography, which should be quantum resistant. So of course, compared to the current public key infrastructure that we have at the moment, it's a little bit slower. So anyway, everything nice. SIDH was accepted to the NIST standardization process. And actually, it made through the third round of selection for this standardization process, but now it's completely broken. And actually, funny enough, apparently it could be like this protocol could be quantum resistant, but not classically resistant. Let me explain you the idea that you can use to describe this, to attack SIDH. Here we follow like the notation, like the work that I've been doing with Cooley Martindale, Lawrence Pani, Giacomo Pope, and Benjamin m0leCon, and there is actually some independent work on the same attack, but with a different description by Kasrik de Croo. So let's analyze again the situation. What's green? Public, red, secret. Let's use this convention. So Bob has this secret key, phi B, and he maps phi B, the A torsion of phi B under this isogeny, the A torsion of E0 under this secret isogeny phi B. Then let's compute an additional isogeny, so mapping onto E0. Let's call this isogeny phi extra. This isogeny phi extra is special. What does it mean, special? I will explain to you what it means. So first of all, we need to be sure that the A torsion on this curve maps onto exactly the same A torsion E0 used by Alice. And once we have this, we need to have the additional constraint that the degree of this isogeny phi extra plus the degree of phi B is equal to A. If this thing happens, and you can make this thing happen if you're an attacker, because I mean you have plenty of leeway on this isogeny. So you know that it should map onto E0, but you can compute any isogeny verifying these conditions. I'm not saying that it's easy to do in practice, but it can be done. Once you have this, then you do a nice trick. Rather than working on boring dimension 1 or elliptic curves, let's see what happens when you take 2 elliptic curves and you glue them together. So rather than analyzing a one-dimensional object, you look to a surface, something like 2-dimensional. So you are adding more structure. You are artificially adding more structure to the scene. When you have this, you can compute a nice two-dimensional isogeny. And the good thing about this isogeny, it will map onto some elliptic product of elliptic curves. But what we need actually to understand is that the first row of this isogeny, because I mean the isogeny between elliptic products can be seen as a matrix, the first row will reveal to you the isogeny phi extra that you computed, but actually this red element here, which means that it's secret, and in particular, you will reveal the minus the dual isogeny of phi b. What's the dual of an isogeny? Well, we don't need to specify what's the dual of an isogeny, but we just need to know that once you have an isogeny, having its dual is basically the same amount of information. So having the dual of phi b or phi b itself, it's the same thing. I mean, like from like an information point of view. So here we have a nice trick, and we recovered the secret key. So this protocol now is completely broken. But now the question that I always like hear whenever I talk to people, like, but is isogeny-based cryptography really dead? Actually, not really, because I mean the protocol SIDH that I described before, there was already a vulnerability on that protocol. In 2017, Petit described an attack on some parameter sets of this protocol. Actually, didn't break the protocol itself, but some instantiation of the protocol. So whenever you have like specific parameters for this protocol, you could already break it, SIDH. But then some people, smart people, decided like, what about if you use this attack, and rather than using like this attack will not completely break SIDH, but what about if we construct a trapdoor mechanism? What's a trapdoor mechanism? A trapdoor mechanism is something that there is a computation, and in order to invert this computation, you need some additional information. So they use this attack to design this trapdoor mechanism, and there in cryptography there is a standard transformation that allows you to compute from a trapdoor mechanism a public key exchange, public key encryption, which is kind of a generalization of a key exchange. So basically, you have something really similar to a key exchange. The protocol here was called SHETA, which stands for Supersingular Encryption from Torsion Attacks. Unfortunately, this protocol was, first of all, a little bit slow, but also it revealed torsion information, which made this, the attack on SIDH, actually, it also breaks this protocol. But that's not the end. Because there have been like new attacks on SIDH, and using these attacks on SIDH, together with two smart people, Andrea Basso and Giacomo Pope, we designed this public key encryption mechanism, which is basically, it's called FESTA, fast encryption from supersingular torsion attacks. Usually I put here like a footnote describing to people that FESTA means part in Italian, but I think that here it's not needed. Most of the people are Italian. So yeah, I think it was like a funny pun. So the idea is quite similar to SHETA. So we designed a trapdoor mechanism, and then we use the attack to retrieve like some secret key, and we apply the transformation to obtain a PKE. I'm going to describe to you how this idea specifically works. So now let's take out all the maths that we need for the SIDH attacks to work. Let's just abstract the maths, and let's just use this object. So whenever we have a secret isogeny phi, and we know its degree d, and we know how to map P and Q under the secret isogeny, then we can recover this isogeny phi if the degree of the order of this point is large enough. So this means that whenever we know like the image of some points under this isogeny, we actually can retrieve the isogeny itself. And this is a nice trick, because from a mathematical perspective, this is basically a representation of the isogeny. Before we used like kernels to represent isogenies. Right now we can use images of points to represent isogenies, and this is actually a neat trick. So what's a trapdoor mechanism? Here I'm gonna wear my hat of my cryptographer hat. I'm gonna explain to you what's a trapdoor function, like really high-level description of a trapdoor function. Basically, it's a triple of algorithms. We have a key gen, f and f minus 1. keygen takes in input like, a secret security parameter lambda and outputs a key pair and a secret key and a public key. Then if you want to evaluate the function f, you just need your public key pk, and then you can evaluate this function at any input x, and the output will be equal to y. If we want to invert this trapdoor function, we use a secret key. And so if we have access to the secret key, we can take the output y, and we can recover the input x. Well, I mean, this is like the high-level overview of a trapdoor mechanism. But what are the properties that you should verify? Otherwise, it's too easy if there are no additional properties that you should verify. So it should be correct, which means if you take a public key and an input x, f minus 1 of sk f pk x is equal to x. That makes sense. And it should be one way. That's really important. So if you are given pk and the output of this function at a certain input x, finding an x such that f pk x is equal to y is actually hard. And this is the hardness of that's something that you should verify for. That's one of the most important properties for a trapdoor function. So let me describe this trapdoor mechanism that we applied for FESTA. So we have an elliptic curve, as in SIDH, and we have 2 points, PB and QB. Then we have a secret key, which will be given by an isogeny phi A, but in addition, we have a secret scalar alpha. And then rather than giving, like in SIDH, we provided like clean torsion images. But if we provide clean torsion images, that means that we can apply the attacks. We have a representation of this isogeny. But what about if we scale these torsion points by some secret scalars? And that's the trick that we applied. We scaled the points on EA by some secret scalar, alpha, and we obtain RA and SA. So the public key, in this case, will be given by the elliptic curve EA together with RA and SA. So now we have a key pair for a secret key and a public key. Now, how does it work for the input? We are given like 2 isogenies, phi 1 and phi 2, and we are given, again, another scalar beta. What do? We take PB and QB, we map PB and QB under phi 1, and we scale it by beta and beta minus 1. And we obtain 2 images, R1, S1. We do the same for phi 2, and eventually we will have an output, this output y, which is given by first elliptic curve E1, R1, S1, and then E2, R2, S2. Now, how do we invert this trapdoor mechanism, this trapdoor function? Well, we look at an isogeny connecting this curve E1 to E2. In particular, this isogeny is given by the dual of phi 1. As I told you before, the dual of an isogeny is equivalent to the isogeny itself, so it's the same amount of information. And then we are given phi A, and composed with phi A and phi 2. And this isogeny is really nice, because it verifies this property. The image of R1 and S1, the image of psi at R1 and S1 is equal to the point R2 and S2 scaled by alpha minus 1, alpha, which is part of the secret key, which means that if you have your secret key, you actually have a representation of the isogeny. And here, scaled by another degree of phi 1, which is actually public information. This means that we are, again, setting of the SIDH attacks, and then you can apply these SIDH attacks again, and you can retrieve phi 1 and phi 2 and beta. And that's actually the idea behind FESTA, the trapdoor mechanism. Now, let's move on a little bit about the efficiency of this protocol. So the efficiency of this protocol actually depends on the computation of the SIDH attacks, which are actually based many computations about these attacks relies on the computation of 2-dimensional isogenies. So there are formulae to compute these 2-dimensional isogenies for specific degrees, but the state of the art of this formulae was not fast enough. So with some people, we decided to look at this formulae, and from a mathematical perspective, we decided to speed them up, and we obtained a faster algorithm to compute these 2-dimensional isogenies. And compared to the previous state of the art, we obtained that the codomain computation is 10 times faster what we had before, and the isogeny evaluation is 20 times faster than what we had before. And so this means that the efficiency of the previous protocol has been increased, but I mean, that's a nice starting point for isogeny-based cryptography, but actually there has been more. There has been like follow-up work. So other people like sped up like the algorithm used by Festa and obtained something even faster, which can actually give like some practical results. But we should not just reduce to trapdoor functions. You can actually look at different primitives. And for isogeny-based cryptography, actually, one of the main selling points of isogeny-based cryptography is that it's really malleable. And rather than just obtaining like public key encryption, you can obtain other more advanced primitives. One of these primitives is like a VDF, verifiable delay function. This is just a sketch of this, of a verifiable delay function that we obtain. But actually, more fun ideas are to come, and I mean, stay tuned if you want to know about the new developments in isogeny-based cryptography. So thank you so much for your attention, and feel free to ask me questions.
Thank you, Luciano, for your very interesting talk. I want to ask you, you have presented the Festa, and which is, you construct your trapdoor function to create an encryption scheme. I was wondering if, can you use this trapdoor function to create other primitives, like, for example, signatures? I don't know, have you ever thought about that?
That's actually a really interesting question. I've been trying. So if you have a trapdoor function, a permutation trapdoor function, then yes, you can obtain a signature scheme, a digital signature scheme. But in the setup of Festa, no, you can't do that directly. But yeah, actually the aim is to apply these ideas for digital signature schemes, given that also the NIST is really interested in digital signature schemes. So that would be like really nice. That's a really a big open question. Yeah, thanks.
Okay, other mathematical problems behind post-quantum cryptography are related with, like, for example, min rank, are related with NP complete problems behind, so they can produce a security proof by reduction to this NP complete problem. So there is something like that here?
Not really. I mean, like the main like morale for believing this, to believe that these problems are hard is that mathematicians have been trying to solve these problems for hundreds of years. They failed, and hence we believe that it's secure. Also, in the case of NP problems, like you have that on average cases, like NP problems are hard, but you might end up with specific instances of these NP hard problems that are actually solvable in polynomial times. I don't know if you can say something like that for isogeny-based cryptography. So I think at this stage you have to believe that this problem is hard enough. And of course, I mean, that's a precarious game that everyone is playing at the moment. But yeah, that's actually a really nice question, and many people are asking that. If you're asking me my personal opinion, I'm not really convinced anymore.
Let's thank Luciano again.